family of these operators. Okay, so when t equals 1, it's the operator we looked at before, although again, in the previous case, we just looked at the self-dual and anti-self-dual parts, but the coefficients are the same. So when t equals 1, well, all right, so when t equals 1, it's the same operator as before, but again, this is looking at the full curvature, so you're subtracting something a little bit more. So if you just check what that means on the level of eigenvalues, it turns out you decrease the eigenvalue because this is a negative term. So the eigenvalue of this operator, when not was a Yang-Mills connection, was non-positive, and I've just decreased it a little bit. So actually, the first eigenvalue of this operator, but it's just an inequality. I'm just using the fact that W plus is less than or equal to W, and if you replace these with the pluses, I know the eigenvalue is less than or equal to 0, so if all I'm doing is increasing the potential here, so I push down the eigenvalue. Okay, so I know when t equals 1, that eigenvalue is less than or equal to 0. When t equals 0, what do I know? Well, when t equals 0, I'm just dropping all of this. This is just the conformal Laplacian. All right, so its sign just corresponds with the sign of the Amobian variant. I'm assuming the Amobian variant is positive, so this must be positive. So the conclusion is that there has to be a t0 somewhere between 0 and 1, such that this operator has a 0 eigenvalue. Just continuity on the parameter t. So that means if I look at this modification of the scalar curvature given by this, what is this, 2 root 6 w plus 3 gamma 1 f plus. So if I look at this modification of the scalar curvature, it implies that with respect to this metric, all right, this is equal to 0. Okay, so the lemma, the lemma implies that if I compute this quantity, so I'm thinking and writing forward and backwards. I have a bad habit of that. Okay, so, all right, so the eigenvalue here is 0, and so that means that there exists a conformal metric for which the corresponding curvature quantity is 0. So there exists G tilde in the conformal class such that this modification of the scalar curvature that I just wrote is an m of 0. Okay. Anyway, the point is you make a conformal choice of metric, and now the scalar curvature is just equal to some multiple of the some norm of the vial plus some norm of the curvature of the Yang-Mills connection. All right, that'll come in later, but anyways, it's a crucial part of the argument. Okay, now let's go back to the second variation. Okay, so remember that if you take the second variation of the Yang-Mills functional, so I vary the connection in this way. I take the second variation. I get 2 times, I'll put a half over here to go to 2. I get the inner product of the Jacobi operator acting on B, inner product on B. So that's the index form. So I want to look at the write the index form out again. So if I write out the index form. So to remind you of the formula. So if you integrate that rough Laplacian term, you get this, right, plus the Ricci tensor of the base acting on the 1 form plus this bracket term. All right. Now basically, okay, so I can do this as a Dirichlet form for some Schrodinger type operator, but the curvature terms I've got to estimate better, and I want to get it back in terms of the scalar curvature. So here's what you have to do. So I'm going to split this up into 2 terms. I'm going to split it up into a term that looks just like the Dirichlet form that operator I wrote earlier, where the leading term is like minus the Laplacian plus 1/6 scalar. So I'm going to add a scalar curvature term here, and that means I'm going to have to subtract the scalar curvature term here. So now I have a Ricci minus 1/6 scalar acting on B plus, let me just write it this way, this inner product of this bracket term. So what I want to do is just do some simple linear algebra estimates of this. Well, not so simple actually. If you want to get decent constants, it's actually a fair amount of work. But I want to estimate all these terms. So if you do that, what you get is let me put this in yellow. So I want to estimate all the garbage in yellow here. So the claim is that all this stuff in yellow is greater than or equal to, you have a very simple estimate, minus 3/4, let me call it z squared, I'll tell you what that is in a second, plus some other constant, I won't tell you, but it's explicit, times b squared. So this is just something about the Ricci tensor acting on B, this is something involving the curvature of the connection acting on B, and this is more or less a sharp inequality of all these. Okay, so z here is the trace-free Ricci tensor. All right, so this will be 0 for Einstein. And beta, I mean, I'm not going to bore you with what it is, but it's explicit. It just depends upon this constant gamma 1 and also T naught. So it's all explicit. So the conclusion is that this Dirichlet form for the index, you could write it as a Dirichlet form for this operator. This acting on B, and a product B, where V is just this collective junk there. So I'll call this V. So mine. Just I put a 1/6 scalar curvature term here, I subtract 1/6, and then all of the curvature terms I collectively estimate this way, and just call that your potential. So here's a Schrodinger operator of the form that I can quote the estimate I erased, right, acting on B, inner product with B. And this Dirichlet form is less than or equal to this Dirichlet form, so if I'm counting negative eigenvalues, I'll reverse the inequalities there. apply this estimate for the number of negative eigenvalues, and what you get is the number of negative eigenvalues of your Jacobi operators. This will be the index plus this is number of non-positive eigenvalues, so that includes the index and the nullity. All right, because it's going to be less or equal to some constant. So I won't write out the constant. All the dependence I did a couple minutes ago, but to remind you, it depends upon basically the Lagrangian invariant and dimension of the structure group of the bundle, and then times the L2 norm squared of V, so V squared, where that's V. Okay. So V squared is 3/4 Z squared plus this constant that I'm suppressing times this. Okay, so this almost looks like the estimate and the conclusion of the theorem, right? So you have the index plus nullity is bounded by some constant times this integral. So there's your energy, but you're stuck with this, right? So what do you do with this? Yeah, so I should have said, so just like the, so we did this, we said that by this eigenvalue argument that there exists a metric for which the curvature, scalar curvature satisfies this condition. So what you do at the outset is you have your Yang-Mills connection, you compute its curvature, you do this conformal change to satisfy this condition, and that's the metric you work with from now on, okay? So this G tilde is actually the metric that's in play in all these estimates here. Okay? It's conformal invariant, so it doesn't matter what metric I do with respect to, so I just do with respect to that one, then run the argument. Okay? Which one? Did I forget to put a 1/2? I should have put 1/2 here, sorry. This should have been a 1/2. Because in the curvature terms are linear, so this had to be linear. Yeah, thanks. Okay, so this is the problematic term, and this is where the choice of conformal metric saves you. Right? So this is the last step. So what you now do is you'll remember that the Euler characteristic shows up in the estimate. So what you do is you use the Chern-Gauss-Bonnet formula. And it turns out that one of the terms is the Z squared. So if you just rewrite the Chern-Gauss-Bonnet formula, you can express 3/4 Z squared, so what are the coefficients? It's minus 12 pi squared times the Euler characteristic, plus 3/2 phi squared, plus 1/16 scalar curvature squared. All right, so what I do is, in this estimate, I take out the integral of Z squared and replace it with these three terms. This is good, that's a topological invariant. This is good, it's a conformal invariant. Wait a minute, I got the scalar curvature term. But as I said a few minutes ago, at the outset, when you begin this process of doing these estimates, you do it with respect to the metric that satisfies this condition. So the scalar curvature already is in terms of the Weil tensor and the norm of the curvature. All right, so you stick that in. And so this term actually, I won't write it all out because that's why the coefficients are so lousy in the estimate, but this can be estimated in terms of W and the norm of the curvature of the connection. So that's why there was this weird cross term where you multiply the Weil tensor times the norm of the connection of the curvature of the connection, because you square this and you get this term times this term is a cross term. So that's the argument. So roll it back into here, and then that gives you the estimate of theorem B. Okay, so let me finish up here. It's been a long day, so I want to try to finish real quick here. I just want to say a few words. I'm not going to drag you to the proof and everything, but say a few words about applying the same idea to get an estimate on the index of Einstein metric. No. Well, no. I'll actually answer that question in just a second. So now, suppose I have a four-dimensional Einstein manifold, and with positive Einstein constant. Because the index estimate that we have relies on positive Yamabe, so I have to do this for positive Einstein metrics. Okay, so now, so Einstein metrics are critical points of the total scalar curvature functional. Maybe I should call it S, so that's a pretty lousy S, but you get the idea. So it sends a metric to the normalized total scalar curvature. So you take the total scalar curvature, and you take the volume, and you put this power there. So you compute the first variation, you get the Einstein condition. Now, if you take a second variation, you learn that Einstein metrics are always saddle points in some sense. So the picture is like this. So here's your Einstein metric. So Einstein metrics minimize the total scalar curvature in conformal directions. So along this direction, that's the conformal class of G. Right? But if you're perpendicular, if you're orthogonal to conformal transformations and orthogonal to trivial deformations, which are given by the action of the diffeomorphism group, so those are known as transverse traceless variations. Right? So then you will maximize modulo a finite dimensional subspace. It's the dimension of the finite dimensional subspace that defines the index of an Einstein metric. Right? So index means the dimension of the space. So I write it as a maximum, but again, it's just maximum modulo finite dimensional subspace. So you asked about the Coulomb gauge. It's the transverse traceless condition is the gauge fixing condition here, because the diffeomorphism group is the gauge group. Yeah. So in this case, where index plus nullity means it's going to be the kernel of the linearized operator. So those are infinitesimal Einstein deformations. So if you apply this, our index again. So I'm not going to go through this, but you cannot use the same. It's a different setup. It's a different Jacobi operator. You're going to make a different choice in conformal metric, but the strategy is the same, and you get the following corollary. This is what I'll end on. So it says the estimate's kind of strange, but it makes perfect sense when you stare at it. The constants don't make perfect sense, but the shape of the estimate. So this estimate is going to say that if you have large index, so in the Yang-Mills case, large index means you have a lot of directions where you can basically go up. So it should be pushing energy up, right? So big index, big energy. For Einstein, it should be the opposite direction. Big index means there's lots of directions to go down, right? So big index should mean smaller energy, which should mean smaller total scalar curvature, and that's what this estimate says. So you get the following. So you have a topological term, the other characteristic, and then here you have 3 plus some constant here. I'll tell you to use in a second. The index plus the nullity of your Einstein metric.